Have you ever wondered why the mass number on the periodic table is not a whole number? We're going to discuss that and the reason why in this episode. So welcome back. This is episode 6 of the Chemistry Made Simple podcast. I'm your host, Matthew Macario. If you're a brand new listener, welcome. This is the show where we help you to get chemistry confident. So why is that mass number on the periodic table not a whole number anymore? Almost certainly the first periodic table you used had a whole number there. Well, there are two main reasons. The first one is that the number on the periodic table that you were looking at was the mass number and not the mass. In other words, it was a simple count of the number of protons plus neutrons in the nucleus of atoms. And the second reason is the existence of isotopes. What do we mean by isotopes? Isotopes are variations of atoms of a particular element, atoms that vary in their mass number. For any particular element, all the atoms, of course, have the same number of protons. That's what defines them as being that element. So to have a different mass number, they must have different number of neutrons from each other, and that's exactly what isotopes are. They're different atoms of the same element, but they have different numbers of neutrons from each other, and therefore those atoms have different mass numbers from each other, even though they're the same element. And it's worth saying that isotopes behave the same chemically. They do the same reactions, with the exception that some isotopes display radioactive behaviour, but behave the same in every other sort of chemical reaction. The most commonly used example of isotopes is chlorine, and we use the example of chlorine for two reasons. Firstly, you probably remember that even on your earliest periodic table, the mass number for chlorine was 35.5, so not even close to being a whole number, and because there's just two stable isotopes that we need to consider. The isotopes of chlorine are chlorine 35 and chlorine 37. That means there are atoms of chlorine that have a mass number 35, and there are atoms of chlorine that have mass number 37. Now they all have 17 protons, that's what defines them as being chlorine. So chlorine 35 must have 18 neutrons, and chlorine 37 has 20 neutrons. Hence the two different types of atom, the two isotopes, have different mass and different mass number. So why have we got 35.5 on the periodic table as the mass? That's not the mass of either of those isotopes. This is down to the ratio that those isotopes exist as. In other words, the relative abundance. The relative abundance means what proportion of all chlorine atoms in a sample are a particular isotope. In the case of chlorine, almost exactly 75% of the chlorine atoms in a sample are chlorine 35, and the remaining 25% are chlorine 37. So if we calculate the average mass of a sample of chlorine atoms, the average is 35.5, and that's the relative atomic mass. But chlorine isn't the only example of elements with isotopes. In fact, every single element has isotopes. Every single element exists as more than one type of atom with different numbers of neutrons. And that's why when you look at the periodic table, you'll see that none of the elements have a whole number as their mass number. Let's consider another example. We're going to consider iron. Now, iron has a mass, depending on the resolution of your periodic table, it's 55.8. As we mentioned, all elements have isotopes, and iron has 4 stable isotopes. Each atom of each of those isotopes has 26 protons, because the atomic number of iron is 26, and the number of protons is, of course, what makes it iron. And we have isotopes of iron 54, iron 56, iron 57 and iron 58. So these have different numbers of neutrons, between 28 and 32. And that's what gives them the mass numbers between 54 and 58 when we total the number of neutrons and protons in each of those atoms. And if we needed to work out what the mass of a sample of iron was, we'd need to know the relative abundance of each of those isotopes. The iron 56 isotope has an abundance of almost 92%. Iron 54 makes up nearly 6%. Iron 57 about 2%. And there's a trace about 0.3% of iron 58. Now, if we do a clever calculation, we can work out that the average mass of an iron atom is 55.8. And that's exactly what happens with all the other elements you'll find on the periodic table as well. So you're probably aware that hydrogen has two stable isotopes, H1 and H2. H1 being by far the most abundant, and hence when we work out the average mass, it's very close to being 1. It's just slightly greater than 1. So you might be wondering how we measure the relative abundance of an isotope. Well, the modern way of doing it is by using the mass spectrometer. You may recall from the last episode, episode 5, that we talked about how the mass spectrometer works and what it does measure, and relative abundance was one of those things. If you haven't listened yet, then go back and listen to episode 5. So what use are isotopes in chemistry? Well, for your understanding, you need to know that they exist. You need to know what relative abundance means. You need to know that the isotopes of an element all have the same number of protons, but differ in the number of neutrons that they have. You also need to know that the relative abundance and the mass of the individual isotopes will enable you to calculate the average atomic mass for a particular element. But what else are isotopes used for? Well, you don't really need to know about this in detail for your syllabus, but we can use isotopes to help us to trace reaction paths in chemistry. And isotopes also have many applications in medicinal chemistry too. I hope this episode has been of interest and of use to you. Don't forget to subscribe. And if you want to get in touch, you can do so by DMing me on Instagram. It's at Chemistry Made Simple. Or you can email me, matthew@chemistrymadesimple.net. I look forward to hearing from you. And I look forward to speaking to you in the next episode. Until then, goodbye. Maybe what we've talked about today has sparked some questions, or you had some questions on this topic anyway, and you're still looking for an answer. Well, I go deeper and answer more questions for the show's patrons after each episode now. And you can become a patron very easily and for about what you'd pay for a coffee. You can find out more by going to patreon.com/chemistrymadesimple. That's patreon.com/chemistrymadesimple. And that link is in the show notes too. Once you're a patron, you'll find that I invite questions after each episode, so you're not left wondering. So I'll see you in that Patreon membership soon. Go there now.